team for Visionb. Hello everyone, I'm Abraham. I'm Ahmed. And Tony. And we're here to present our company, Visionb. We're starting with a little story point. So in 2018, I had an eye surgery and with 3 days recovery time. During these 3 days, I was covering my eyes and I couldn't see anything. So I was looking for any means of entertainment. The only thing that I found was audiobooks, and it was torture to listen to audiobooks for 3 days straight. So I was thinking about, that got me started thinking about those who are permanently blind and if they have any means of entertainment. So after doing a couple of research, it was found that in 2015, out of the global population of 7.3 billion people, 253 million people had some form of visual impairment. And out of this, 217 million people had moderate to severe visual impairment. And 36 million people were totally blind. And it was also found that soccer was one of the most popular sports in the world. And more data suggested that in the UK, out of 5.1 million people that were visually impaired, 43% of them were soccer fans. And so, moving on, I'm going to be talking about the problem. So, when we delved into the market, it was found that there existed very few number of devices that actually catered to the visually impaired for field sports. And we also found that the existing devices were just basically all-around assistive tools and not really catered towards the experience that the visually impaired had for field sports. And so we decided to change that with our invention, the Visionb. So our device would basically allow the visually impaired individuals to experience field sports and the sport that we chose, soccer. Here you can see our demonstration of the product. So in a nutshell, how this works is that we would have our camera setup over on top of a soccer field, which would relay the position data of the soccer ball onto a microcontroller unit in the device. And this microcontroller unit would then move the end effector, as you can see here, along, and that would lift up a couple of pins showing the exact location of the ball in real time. And here we have the competitor analysis. So the closest to competitors that we have is the Iris Vision headset and the descriptive commentary services. None of them are specifically designed for the blind and for field sports. So our device is specifically designed for that function. And we also provide accurate real-time power representation, whereas the others don't. The only major drawback that we have is that ours is not an all-round assistive tool.
Okay, guys. So this is the map for our flow chart. So we have our main components, the camera that's gonna record the object, the soccer ball object on the soccer field, and then send the data to an object detection algorithm called YOLO. The YOLO will extract the XY coordinates of that object and send it to a microcontroller. The microcontroller will further calculate the revolution of the rotational position, and then convert that to a steps. So the stepper motor can take it as a signal and then simulate the position of the soccer ball on the fitness plan. And then this is our design. So for the electrical design, we have this is our motherboard. So it has got the microcontroller. It's a ESP32 for encapsulation security payload, and the microcontroller is a 52 bits microcontroller and has 42 megahertz of frequency, so it's very fast, and has Wi-Fi connectivity to send the position of the ball over wireless. And not pretty. Okay, so also here we have two motor drivers. These are the DRV8825, specific for bipolar stepper motors. We have the voltage regulator that's going to take that input voltage and then regulate it to 5 volts to run the ESP32. And this is our main schematic diagram for the electrical wiring. We have the ESP32 here, it's an 72 GPIOs microcontroller, so we can have a for future expansion. and then sends only two signals to each motor driver, which are the direction signals. And then we have also the AC to DC converter that takes just a one outlet and then converts it to a DC voltage of 16.8 volt to run the motors, and also keep the voltage regulator, the buck converter, to have 5 volt voltage. And we have also a battery gauge before the plant to know how low is the battery, and we have a vibrator, a rumble motor to send vibration. And our solar motor, the design uses a gantry system. So this is our stepper motor. It's a NEMA 17 hybrid, so it has the advantage of a servo, brushless DC motor for speed, and it also has a torque capabilities, and it's most accurate for positional presentation. And we have custom designed this gearbox to translate the horizontal motion to a vertical motion to drive the mechanism. Again, so this is our motor driver here, the RB855. Yeah, so it's a very compact in size. It's the size of a balloon, and it's not very light, so it's best for our low profile. And at the end, you can see here at the very back, it's our rumble motor. So we have two motors. One has a centralized on the shaft to send vibration feedback to the user when the ball enters the motor. And these are the sensors. So are they placed on each end of the mechanism? So when the carriage, the end effector, reach both ends, we can know where the position of the end effector is at that time, so it doesn't just go, it will just bounce off.
So next, I'm going to be talking about the mechanical subsection of our device. So starting off, we have the case. So we made the case out of PLA plastic for this prototype, and for later mass production models, we'll be using injection-molded plastic. The reason for choosing PLA plastic is because it's very lightweight, it's not toxic, and it was easily printed using the in-house printers at Visionb. It was also cheap to manufacture, and it's very easy to prototype. And next component that we have is the interactive pin board, and the system that we use is a pin matrix system, which allows for a high resolution of tactile feedback. It also distributes the load of the pins uniformly on the user's hands when the user uses the device. And the pins are very easily replaceable in case they break, and it's also it has very low cost of production.
And now I'm going to discuss the pin and end effector interaction. So the end effector and pins were designed as a cannon forward pair. That's to translate or convert the vertical motion, the horizontal motion of the end effector to vertical motion. And also this reduces the thickness of the device, the total thickness, and the mushroom shape allows for like more distribution on the user's hand of load. And here is our pin assembly. So we have a total of 408 pins, and each pin consists of 4 parts, two ball heads, and one brass threaded rod, and one aluminum tube. The total length of the pin is 2 centimeters, and the diameter of the ball is 4 millimeters. And this again is designed for based on the distribution and the resolution that we wanted to achieve for the user's hand. And here is our pin head selection. So why we use both? The reason we use both is to prevent the pins from falling out within the device without restricting its movement and keeping it free to move. The other thing is to make the user side safe on the user's hand, and the other one is to slide on the end effector mushroom shape. Here is a table for our selection of the pins. So our first choice was the acetal resin, which is very slippery with 0.25 coefficient of friction, and is easy to machine and drill, and it has medium durability and low cost. The reason we didn't go with this one is because it was out of stock for more than 10 weeks, and we had to go with our second option with the 316 stainless steel bolts, which are slippery but needs lubrication and is hard to manufacture. The third option was the low carbon steel, which is really hard to machine, and, but it's the cheapest option in this list. However, during our machining, an incident happened, and the drill bits that we were using for the CNC machines broke, and we couldn't continue drilling or tapping these bolts, so we had to go with the PLA plastic, which is our fourth rank choice. Here's our end effector holder. As you can see, the end effector is machined out of aluminum, and the end effector holder is made of PLA plastic as well. It's 3D printed and custom made. It's lightweight and has low friction to the pins. Here is our gantry system, which is a mechanism called Corex Y, which is Cartesian mechanism, Cartesian movement, linear motion mechanism, which is used in 3D printers and CNC machines. The advantage of the Corex Y mechanism is that it has high accuracy and high precision, and also allows for stationary motors, which means that we will not worry about the moment of inertia of the moving one. Here is the equations of motion of the Corex Y mechanism. So if one of the motors moves, only it will move diagonally, and if both of them rotate in the same direction, it will move in Y direction, in X direction, and if we rotate in opposite direction, it will move in Y direction. So these sets of equations turns the X and Y coordinates that we get from the YOLO algorithm, which is discussed later, and turns it to number of steps and the direction of steps that will be sent to the stepper motor control machine.
Right. For the software section of our device, the main challenge was using the object detection to gather the coordinates that we wanted in a usable way for our board, and then sending the scaled data from the photo representation to the board. So the first part of that is to get camera footage. As you can see here, even with a lower quality camera, the object detection algorithm used, YOLO, is still able to pick up the objects, the sports ball and the person. With using a higher quality camera, it'll increase the usability of the data that it gets. And here you can see the compiled frames and X and Y coordinates from a run of our YOLO algorithm, where we extracted the frame number and the X and Y pixel location from a video. The reason we chose YOLO is because it's an open source, free to use algorithm. It's very easy to implement and use, and it provides us the exact data that we want for our device. So going forward, for our market strategy for our device, we're hoping to partner with sports organizations like FIFA and sports broadcasters like ESPN, which FIFA is in charge of the sports, soccer organization around the world, and they have the final say. So if we can partner with them, that'd be great. And the sports broadcasters have the video footage, which we want to move into using that footage for our device. And just to briefly go over our kind of an estimate for the best case for our cash flow and their cost. We estimate with about a $69,000 investment. We can generate in the first 2 years net present value of about $200,000, an IRR of approximately at 297%, and an ROI of 291%.
And to conclude, we'd like to thank all of the members helping us in the creation and the development of our product.
There's a video on Good Devil.
Posting in the demonstration of the vision board working principle, in which a gantry system elevates a series of pins representing the XY coordinates sent to the board. In this cross-sectional view of the board, it is shown how the end effector of the gantry system pushes the pins as intended. The blind user of the vision board can place both their hands on the pin display. Then the pins representing the location of the ball will be pushed to their hands to give them a feeling of the current location of the ball. This video demonstrates the movement of the pins, while the uppercase is fully installed. As you can see, the end effector's horizontal movement pushes the balls vertically as intended towards the user's hands. In this video, we will be using an advanced object detection algorithm called YOLO V5 to track the soccer ball's location. As you can see, the algorithm has successfully detected the ball's position in the video. We processed the video at a resolution of 1080p with a 50% confidence rate. However, due to the low resolution of this particular video, there are instances where the ball may not be detected in some frames. To improve the ball detection accuracy, higher processing power will be required to handle higher frames per second. Nonetheless, YOLO V5 is a reliable algorithm for detecting objects and has performed well in this video. Here is another example of using YOLO V5. As you can see in this video that we recorded using a Samsung HMXF90 camera, the algorithm was able to detect the ball and the person with high accuracy.
Thank you.
Hi, guys. So my question would be, what were some of the biggest unexpected hurdles you encountered? Like I see you built a gearbox. Did you plan to build a gearbox in the first place? Did you end up having to build a gearbox, for example? So what were some of those big surprises and how did you overcome them?
So for the gearbox, we actually initially planned to design the gearbox, and the reason for that, because we didn't use encoders, so we were only relying on the precision of the stepper motor. So we just made that so we can keep a place for adding an encoder without having to increase the thickness of the device, because it's already thick enough. So one of the other things that we encountered was the machine, like as I said, an incident happened and we broke all the filaments. So now the all this that we're using in the PLA is very rough, so we have to use all the cancel all of that, and that makes like the motion of the interaction between the gantry system, the end effector, and the pinballs this interaction. So we have to, and also the third one is that we burned two driver motors.
So like I'll explain that. So just like last week, last Friday, we had a talk and ready to just like further tune particular data that's sent from the algorithm, and then like we had two wires coming out of the breadboard, single wires that should keep the power supply. And everything went to the power. My laptop, all the data has nothing backup.
So we had to code.
So we had like we had to sit down. He gave me his laptop. We're good there.
So we had to code one the driver to
recorded everything and then I got it working, and then just couple hours ago. I uploaded the code, and so I pushed the buttons, I changed the code, so they push button before telling me, and the poly went loose.
So you had a real world experience there. That's how it actually goes. Yeah.
Thank you.
So I'm interested in the ball tracking here. I mean, that's a non-trivial problem. I know YOLO does it, but there must be some work that you have to do for fiducial points on the field or where the ball is, or does YOLO just do that for you?
So you can kind of filter out the different kind of objects. Right now we're trying to working towards putting in the kind of parameters that single out a ball better, and kind of footage is required to have that best kind of results. You also see, you kind of saw a bunch of jumping around in that video. There's a bunch of outliers that are produced, so we want to make sure that we're only getting the coordinates that are from like the ball. So if there's an outlier, you just eliminate that, just take the one that was closer to the ball from the last prediction. For tracking the outline of the field itself, it doesn't, so we have to set up the camera in a way that's only getting centered on the field that we want to kind of predict at the moment, since right now we only want to use a stationary camera. But then after that, we kind of want to move towards the live streams, where the camera is moving and might not show like just the field. That's something we have to work towards.
Yeah, it's more of the scenario I was thinking. If you're taking a feed from a game directly, cameras vary, all that. So, yeah, okay.
To add up to that, like in FIFA World Cup Qatar last year, so each field had 26 cameras on the field, and the balls were instrumented, and they were actually getting the location of the ball. Like we didn't expect that they will actually use instrumented balls, because when we started this project, we said we were going to instrument ball, and we said no, FIFA. There is no way FIFA was going to accept that. And then when FIFA in Qatar, they actually used instrumented ball. So if we partner with them, we can actually get that location of the ball without having to worry about the camera. So that's something that can work.
We also forgot to mention we will be using pre-existing scripted commentary that already has been implemented in the last World Cup. So we will be using together with our device for the experience of the.
So we have an opportunity for one more question.
Chris.
Just one.
All right, Chris, go for it.
I had a question. Soccer is a three-dimensional game, and what you have is kind of like a one bit in a two-dimensional array. You're moving that one bit. You get soccer. But with a tactile sensor, could you have another dimension? Like I'm thinking like a CNC machine where you can have X, Y, and Z control, and that could give you another dimension.
So that's our initial plan. We have 3 dimensions, and we were going to do that. But the only thing is, because our product is already thick, we didn't want, if we add the 3rd dimension, it is getting thicker. We wanted to decrease the thickness actually, and it became thicker because of the cost and size constraints. Because whenever you go like with smaller pieces, it goes significantly higher in terms of cost. So we have to decrease that. So one of the things that we said we're not going to do is the 3rd dimension that we wanted to do.
We had decided initially, but didn't work for the contact.
And I had another thought as you're doing your presentation. It's very interesting. But when I think of tactile sensors, for example, I have 2 hands and I have 10 fingers, 2 feet and 10 toes, I guess, as well. And is there a way that instead of having a single bit, you could have multiple bits that are kind of wiggling around?
So it's there for
and then have another dimension. Visualization.
Yeah, I don't want to this because I know someone here is no biomedical, but from my experience, from my research, the small research front, and one preliminary research we've done we have found that the sensory on the palm of the hand on this side is the most accurate sensory, and they are placed in within, like, you can get 2 millimeter senses. So this one is the most accurate presentation been used as a bell display initially by the blind. So we had to just like use that pre-existed task on knowledge they already acquired to start like demonstrating.
I'm gonna add on that. So to use more than one, then we need to use like solenoid pins. So that's one thing that we considered at the beginning. But again, the cost constraint. Each solenoid costed $3 from China. That means we have 408. That means $1,200 just for the pins. So again,
There's audio to represent. So something because you don't care.